What if I told you that Starship doesn't just fall back to Earth, it flies back? While most spacecraft re-enter like stones wrapped in heat shields, SpaceX's Starship behaves like a skydiver, gliding through the upper atmosphere on 4 massive steel flaps that control its fall, direction, and speed. These flaps aren't just pieces of metal, they are one of the most complex aerodynamic systems ever put on a spacecraft. And getting them wrong could mean total destruction before Starship even has a chance to relight its engines. Starship's re-entry phase is one of the most visually stunning moments in modern rocketry. But behind that cinematic belly flop is raw physics, lift, drag, moment arms, and feedback control. In this deep dive, we're going to break down exactly how these flaps work, how SpaceX controls such a massive vehicle with just 4 moving panels, and why mastering this part of flight is the key to Starship becoming fully reusable. Every re-entry begins with one universal truth: energy has to go somewhere. When Starship is in orbit, it's traveling at roughly 17,500 miles per hour. The challenge is to slow that down to 0 without burning up or losing control. Traditional spacecraft like Apollo or Dragon rely on a heat shield and a stable capsule shape. They come in at a set angle and let drag and ablation do the work. But Starship is different. Its upper stage stands 165 feet tall, with the full stack reaching about 400 feet when paired with the super heavy booster. It's made of stainless steel and designed to be used again and again. A blunt capsule approach simply won't work here. Instead, Starship enters belly first, using the broad side of its body to spread out the heat and create immense drag. By exposing a larger area to the atmosphere, the heating rate is distributed over a much greater surface, preventing any single point from exceeding critical temperatures. It's like spreading your weight across thin ice. Wider surface, less stress per inch. However, the problem with going belly first is that you lose natural aerodynamic stability. Capsules like Dragon are designed to always face the right way due to their shape. Starship, on the other hand, is more like a flying brick. Its shape doesn't naturally keep it oriented correctly. Without some form of control, it would start tumbling uncontrollably. That's where the flaps come in. Think of Starship's 4 flaps as its arms and legs during re-entry. 2 are mounted near the nose and 2 near the tail. They're huge, each one about the size of a billboard, and made of stainless steel with reinforced hinges that can survive the hellish temperatures of re-entry, reaching up to 1,800 degrees Fahrenheit on the windward side. Their purpose isn't to provide lift in the airplane sense. They don't fly Starship upward. Instead, they control the distribution of drag forces along the vehicle's body. By adjusting the angle of each flap, Starship shifts where the aerodynamic forces act relative to its center of mass. That change in force position generates rotational torque, pitching the nose up or down, rolling left or right, or yawing sideways. The physics is straightforward but powerful. Each flap experiences a drag force proportional to air density, velocity squared, and its projected area. When one flap moves, it changes the local airflow and alters the total aerodynamic moment. Even small deflections, just a few degrees, can change Starship's attitude dramatically. During descent, onboard sensors constantly measure velocity, angular rate, pressure, and temperature. A flight computer runs predictive models hundreds of times per second to determine how the atmosphere is interacting with the vehicle. Then it commands each flap individually to adjust in real time. This makes Starship an active control vehicle. It's not stable by default. Its stability is created by continuous flap motion. Without constant corrections, it would immediately lose balance and spin. Essentially, the flaps act as dynamic stabilizers in an inherently unstable aerodynamic regime. Now let's talk about the famous belly flop maneuver. When Starship begins re-entry, it's initially vertical, tail first, with engines facing forward. As it starts encountering denser air, the ship performs a controlled flip to a horizontal orientation. This is the belly flop. In this phase, the vehicle maximizes drag. Instead of slicing through the air like a dart,
It spreads itself wide to slow down faster. The belly of the ship acts like a massive air brake, and the flats keep it perfectly balanced. Each flap continuously moves to counter any roll or pitch deviation caused by uneven airflow. Imagine dropping a playing card horizontally. It wobbles, flips, and spins chaotically. Now imagine that card has small fins constantly correcting its motion. That's Starship in a nutshell, a falling card that keeps itself stable with intelligent control surfaces. Why go through all this trouble? Because controlling how you fall directly affects where you land. The flap system allows Starship to steer itself during reentry by shifting drag forces. By modulating its orientation, Starship can control its cross-range distance, meaning it can literally glide sideways dozens of miles to align with its landing site. This flexibility is crucial for operational missions. Unlike Falcon 9, which lands using grid fins and engine burns in a mostly ballistic trajectory, Starship's reentry is a guided fall through aerodynamic control, reducing the need for large propellant reserves to steer with engines. Here's the part where the physics gets even more interesting: energy dissipation. Starship needs to shed an enormous amount of kinetic energy as it descends. The majority of that energy turns into heat and is carried away by the atmosphere. But the rate of energy loss is critical. If Starship descends too fast, it risks overheating. Too slow, and it loses aerodynamic control at higher altitudes. The flaps fine-tune this balance. By increasing their angle of attack, they boost drag and slow the descent. By flattening out, they reduce drag slightly, allowing the vehicle to maintain speed where necessary. This means the flaps essentially act like variable air brakes, modulating how quickly Starship bleeds off energy during reentry.
At these altitudes, air density is changing rapidly, from near vacuum at the top of the atmosphere to thick, turbulent flow near sea level. The control algorithms must continuously adjust for these changes. SpaceX engineers designed the flap actuators to handle extreme torque loads while remaining responsive enough to make millisecond corrections. And it's not just about keeping the vehicle balanced. The way Starship dissipates energy affects where it transitions to engine reignition. That's the ultimate payoff of all this precision. If Starship manages its fall correctly, it'll reach the ideal altitude and velocity for the final flip and engine burn. The final phase of descent, the flip and burn, is where everything comes together. As Starship nears the ground, usually a few thousand feet above the surface, it pitches from its belly-down orientation back to vertical. The lower flaps drive the rotation, while the upper flaps assist in counterbalance. In this instant, aerodynamic control transitions to engine control. The Raptors ignite, stabilizing the vehicle for a propulsive landing. The accuracy of that burn depends entirely on how well the flaps manage the prior descent. If they've done their job, Starship is perfectly aligned and moving at just the right speed for a smooth touchdown. There's another layer of brilliance to SpaceX's flap design: simplicity. The flaps are not actively cooled. They're made from the same stainless steel as the hull, which has a high heat tolerance and good strength retention at elevated temperatures. During reentry, the windward side of the flaps experiences temperatures up to 1800 degrees Fahrenheit. Instead of radiators or tiles, the steel simply absorbs the heat and radiates it away naturally. The hinges, however, are a different story. They're shielded and insulated because mechanical joints are more vulnerable. Engineers use heat-resistant materials and tight tolerances to ensure those hinges can move freely even after multiple re-entries. What's remarkable is how the system has evolved. In early prototypes like SN8 through SN15, SpaceX used initially simpler actuated flaps. Flight tests in 2020 and 2021 proved the concept worked. The belly flop and the flip maneuver both succeeded, even if the landings didn't. With each iteration, SpaceX refined the control algorithms and flap geometry. Today's Starship features stronger actuators, better sensors, and more precise software control. The flaps can move faster, resist greater aerodynamic loads, and hold position even under extreme plasma pressure. As we move toward operational flights, these refinements are crucial.
So what makes Starship's aerodynamic approach revolutionary? Most spacecraft are designed to survive re-entry. Starship is designed to fly through it. It doesn't just fall, it maneuvers. It doesn't just survive the atmosphere, it uses it as part of its control system. By integrating aerodynamic control into the vehicle's architecture, SpaceX eliminates the need for complex reaction control thrusters or huge propellant reserves for orientation. Everything is handled through the physics of airflow and computer-driven control surfaces. It's efficient, elegant, and brutally effective. The cliffhanger question is this: will it scale? The real test isn't just Earth re-entry, it's Mars. On Mars, the atmosphere is 1% as dense as Earth's. The same flaps will behave differently, producing far less drag and control authority. SpaceX engineers are counting on the same fundamental physics to still apply, just with different parameters. The idea is that by using a combination of flaps and limited engine burns, Starship can achieve a controlled Mars landing just like it does on Earth. Future orbital tests will refine this aerodynamic system's performance, building on the successes of Flights 10 and 11 in 2025. If it does, we'll have the first fully reusable spacecraft in history capable of re-entering from orbit multiple times with only minor refurbishment. In the end, Starship's flaps represent something deeper than clever engineering. They're a symbol of SpaceX's philosophy: iterate, test, and learn from physics itself. Every movement of those giant steel arms during re-entry is a dialogue between engineering and nature. And if you think the re-entry physics are mind-blowing, just wait until we dive into how the Raptor engines coordinate with that final flip. It's a dance between fire and air that no spacecraft has ever mastered before. So, if you enjoyed this deep dive into the physics behind Starship's aerodynamic control, make sure you're subscribed, because in the next video, we'll break down the flip maneuver itself, the moment when 120 tons of falling steel rotate 90 degrees in just a few seconds to stick the landing. Until then, keep looking up, because every